Hi viewers, welcome to LMS Solution. Today we are going to see about step-by-step implementation of single-stage grid-connected PV system. So for that we need PV array. So just I am going to type PV array. So here we are going to design around 100 kilowatts grid-connected PV system. So first we need to fix the number of series connected model and a parallel string for generating around 100 kilowatts power from PV. So here you can see that the voltage at maximum power point is 29 for single panel and current at maximum power point is 7.35 amps. Okay, and here that means here we are using single stage, that means that PV directly going to be connected to the inverter. So here I am going to consider the voltage across that inverter, which is equal to 900. So first we need to find out the number of series connected model. So for that you have to divide this 900 by this 29. So then you will get the number of series connected model. Okay. So first we have to calculate that value. So 900 divided by 29. So we are getting around 31. So next to process you have to find out the parallel string. So parallel string can be calculated based upon the power rating. So here we are going to design for a 100 kilowatts grid connected system. So I am going to use 100 e power 3 divided by, the formula is ns into VPV single panel voltage into NP into IMP. Okay, so here the series connected model is 31, the single panel voltage is 29, and then the single panel maximum the current at maximum power point is 7.35. So 7.35 you have to calculate that. Here you can see that here we are getting around 15, right? So the number of the parallel string we needed is 15, number of series connected model we need 31. So totally we are generating around 100 kilowatts power. So that can be seen in the PVIV characteristics. So here you can see that for 1000 watts per meter square, right, we are getting around 99.11 kilowatts. Okay, it's around 100 kilowatts. So next we need to, that means we need to operate this PV panel at maximum power point. So here we are going to use P&O MPPT. So already we have the P&O MPPT. So here you have to click this one. So this is a P&O MPPT. So here you need to measure the voltage and current of the PV panel, and here you need to provide 4 reference values. That means V reference maximum is 1125. So 1125 nothing but open circuit voltage of the PV panel, and then V reference minimum will be, that means voltage at short circuit current. And then here initially we have to provide the initial voltage, reference voltage from that P&O MPPT. So here I am going to mention the reference voltage from the P&O MPPT is 900, and then small change in reference voltage, here I am going to consider 1 volt. Okay, and then here you have to fix the 3 variables. That variable nothing but V volt, P volt, and V reference volt. So these are nothing but previous instant PV voltage, PV power, and the reference voltage. So initially you have to fix the value for this, the previous instant PV voltage, power, and the reference voltage. So the previous instant voltage, PV voltage, and power will be is fixed initially is 0, and then previous instant reference voltage is fixed at the initial reference voltage. So next you have to calculate the power of the PV. So by using this formula V into I. Next you have to calculate change in voltage del V, change in power del P, by using this formula V minus V volt and P minus P volt. So initially you have to check the change in power whether it is equal to 0 or not. If it is equal to 0 means already PV panel is operated at the maximum power point condition. Okay. If suppose is not equal to 0, next you have to check the dP is less than 0. If dP is less than 0, next you have to check the dV is less than 0 not. If dV is less than 0, we need to increment the reference voltage. Otherwise, we need to decrement the reference voltage in order to bring back that PV power to the maximum power point level. If suppose this condition is not correct, right? Again, we need to check this dV is less than 0 or not. If dV is less than 0, we need to decrement the voltage or increment the voltage. So in order to bring back that PV power to the maximum power point. If suppose if dB equal to 0 means, so you have to keep that V reference voltage equal to V reference, that means previous instant reference voltage. Okay, so next you have to check the reference voltage, the limit, right? You have to check the limit of V reference between V reference max to V reference minimum. So both are that means if this condition is not satisfied, right? So then we need to that means we got to keep this reference voltage at the previous reference voltage. Okay, so next process will be you have to override that reference, that means previous instant current instant reference voltage and current instant PV voltage and PV power to the previous instant PV voltage, power and the reference voltage. So it will be keep on executing in order to get the maximum power from the PV power. Okay, so for that we need to provide the detail. That means first I am going to use bus selector for selecting the input from the PV measurement. So here I am going to select VPV and IPV, and then that will be given to input for that MPPT algorithm. So here I am going to feed this detail VPV, IPV, and then I am going to use go to block. So here we are going to measure, that means VPV, and here we are measuring IPV. So just change to IPV, and also here we are measuring the power. So I am going to use product. So here I am going to mention which is equal to PPV. Okay, PPV, and then this is reference voltage from that MPPT. So I am going to mention it is reference voltage, V reference. Okay, so next we need to connect this. Before that we need to connect two constant block. So one is for irradiation, another one is for temperature. So initially I am going to make irradiation equal to 1000 and temperature equal to 25 degree Celsius. So next we need to connect this PV panel to the inverter. So before that we need to use some filter. So for that I am going to use series RLC branch. So I am going to use this value which is equal to 1000 microfarad. Okay, and then I am going to use universal bridge. And then I am going to rotate this one, and then I am going to use IGBT diode, and then I am going to rotate this up and down. So here I am going to connect this one, and here also I am going to connect this. So after that I am going to use 3-phase, that means after inverter we need to use LCL filter. So for that I am going to use 3-phase RLC branch. So before that we need to measure the voltage and current of the inverter. So for that I am going to use 3-phase voltage and current VA measurement. So here I'm going to use label concept. So here this is V inverter, this is I inverter, okay, and then I'm going to connect this here and here also, and here I'm going to connect this RLC branch. So this one is L, and next we need another inductor. So next we need capacitive element. So I'm going to connect like this. So next we need to connect this as delta concept. So sorry, this will be connected plus like a common point. So this will be C and this will be L, okay. So next we need another measurement. So in the grid side, so next we need to use 3-phase voltage source. So for that I'm going to use this one, and then I'm going to rotate, and also I'm going to flip the block. So here I'm going to connect this one, and this label will be changed to VABC and IABC, and here we need to fix the voltage is 400, and here I'm going to fix frequency is 50, and then here I'm going to fix 400, okay. So everything over, we need to provide the value for this L, and this C, okay. So further we have that design equation. So this is design equation. So here we need to feed the detail of S, VDC, FSW, VAC, F. These are the design equation for LCL filter. So I'm going to execute this one. So here you can see that is the L1 value. So copy this one and paste it here, L1, and then here you copy, this is L2. So paste it here, L2, and then this is C. So copy this one, and then here you have to paste, okay. So next process, we need to create the control logic for this inverter, okay. So for that I'm going to use front block, and here I'm going to measure VABC, the mean grid voltage, okay. And next I'm going to use PLL for generating the omega t, because here we are going to apply feed forward decoupling control concept, okay. So here I'm going to fix the frequency is 15, and here I'm going to use go to block. So go to block, here I'm going to mention is omega t, okay, phase angle with respect to time. So next I'm going to use ABC to DQ not apply that decoupling control concept. So input for this is VABC, and then this is omega t, and output will be DQ naught. So here I'm going to use D max, and this will be free output D max. The first one is VD, okay. So this is VD, and then the second one is VQ. The same way we have to take the current, right, inverter current. So I inverter, and then you have to use ABC to DQ naught, and then you have to use this same omega t, and this will be current, right. So here you have to use go to, and then here you have to type ID, and then this is IQ. Okay, so next to process, first thing is we will go for voltage control. So you have to take this reference voltage and you have to take PV voltage. That means we have to apply the control logic for a direct axis parameter. So first we need to compare this both voltage sum, just you have to use sum and then connect like this, plus minus, and then you have to use PID controller, and then you have to choose discrete and PI controller. Okay, and then we have another summing block we need. So this is for a DC link voltage control. Okay, so this will be provide some current reference based upon this DC link capacitor. Okay, so next you need to measure this PPV. That means you need to take the power of PV panel. So that should be multiplied by 2 by 3. So that means we are converting that PV power to the single phase power, and then you have to use divide function, and then it going to be divide with this VD. Okay, so then you will get the single phase current in the form of a direct axis. Okay, so here you have to add this one. So finally we will get the ID reference. So this is a reference current, ID reference current. Okay, next to process, you have to compare this reference current with the ID, and then again you have to use another PI controller. Okay, so next to process, you have to apply the decoupling control concept, right? So I am going to use another summing block. This block having 3 plus. So this one from this PA controller. Another one thing is VD, and another one thing is from IQ. IQ should be multiplied with 2 pi omega L, right? So here I am going to use gain block. So here I am going to use 2 into pi into 50 into L value. So L value is nothing but L1 plus L2. So here you have to copy this one. So this is L1 plus L2. So you have to paste it here, 2 pi FL or omega L. Okay, that will be added here. So after that we are getting that means you have to multiply it with the 2, and then you have to divide with the VPV. Okay, so you have to divide with the VPV, and then here we will get a control signal in the form of direct axis. So this is the direct axis control. So next we go for a that means quadrature axis control. So for that means here we didn't control that IQ. That means we are going to maintain IQ equal to 0. So just I am going to use constant. The reference value for that IQ control is 0, and then you have to copy this one IQ, and then here you have to take this summing block, and then you have to use this, and here you have to take this summing block, and here you have to take VQ, and here you have to take this ID. So ID should be multiplied with the omega L, and then given here. So here you have to change the sign. Okay, so next you have to use the same. That means you have to multiply with the gain 2 and divide with the VPV, and here you will get the that means control voltage in the form of Q axis. Okay, so next you have to combine. So for that I am going to use mux. So here you need 3 input mux. So first input will be provided here, second input should be given here. So here you will get a VDQ naught. Okay. So next we need to convert DQ naught to EBC, and for that we need this omega t. So here I am going to connect this, and then this should be processed via PWM generator. So for that go to measurements, pulse generator, and then 2-level generator, PWM generator. So here you have to provide frequencies 10 e power 3, and then I am going to use go to block, and this is nothing but PWM pulse for that inverter. So finally we are giving this detail to here, that means PWM pulse will be given here. Okay, I think everything is over. That means MPPT control, inverter control, everything over. So next we need to provide power GI, right? So we are using specialist detail, and then I'm going to use a discrete, and then I'm going to fix sample time is 1 e power minus 6, and here you need to provide break algebraic loop in the internal model. Okay, next you go for measurement. So here I'm going to use scope. So the scope for measuring grid power, grid voltage, current and power from this PV inverter. So here I am going to use from, so here we are using VABC, that means grid voltage, and then here I am going to use high inverter, that means current of inverter, and then I am going to use measurements, and here I am going to use this one. Okay, for measuring the power from that inverter. Okay, and same way we are going to measure PV voltage and PV current and PV power. So this is for inverter, and this is for PV, and one more thing, we got to measure the power of grid also. So this is grid, and here you need to change IABC. So everything is clear. So here we need to simulate this model. So what actually we are getting in the every scope, right? So here you need to change the number of, that means scope layout first. So here I am going to change scope layout to 3. So here also I am going to change the scope layout equal to 3, and here also I am going to change scope layout is 3, and also here we are measuring the logging the data in order to check the THT of the current, right? So I think everything is okay. So now I am going to simulate this model. Okay, here the problem is we are using single phase PLL, so we need to use 3-phase PLL. Okay, so just you have to change this to 3-phase PLL. So that's why we are getting that error. Okay, so now you have to simulate this model. So we are not getting the proper output. Okay, so because we are not tuned that controller, right? So because we are getting the current, right, power will be distorted. So here I am going to tune this PA controller. So I am going to tune this PA controller. So for that I am going to use PAD tuner app. So here I am going to select identify new plant, and here I am going to use simulate data. So initially I am going to fix the offset equal to 0.5, and then amplitude I am going to fix 0.3.8, and then I am going to simulate this model. Okay, so the simulation will be carried out for 2 times. Okay, so we will wait for completing that simulation. That means here we are going to identify the data of the PA controller. Okay, so by identifying the PA controller data, so we need to create the transfer function for our system. After creating transfer function or estimating the transfer function, okay, based upon that transfer function, you have to design the controller parameter like Kp and K. So this is will be happen in this PAD tuning app. Okay, so we'll wait for a completion of this tuning process. So it will take some time, right? So here the first run is completed now. Okay, so it will be simulated for another one time, right? So second time it will be run again. Okay, and then after completion of this simulation, we can see this identification data here, right? So we will wait for completion of this second simulation. The second simulation run also going to be completed now. Okay, after completion you can see here, right, identification data. Okay, so we will wait for that. Yeah, now you can see that this identification data from that to simulation run, right? So here I'm going to apply, and then I'm going to close. So next I'm going to estimate the transfer function for this identification data. So this is completed now. So now I'm going to apply. So here you can see that actually now we are getting this P and P and K value. So here I'm going to change this response time to very slower, right? And then I'm going to apply now. Now I'm going to simulate the model. So here we will get the value of kpk. Now I am going to simulate this model. So now we can see here, right, this oscillating, right? But not settled to some voltage level, or we can see that power is also oscillating now. So now I'm going to stop this one. Again I'm going to slow down the process, and I'm going to update the block of kpki, and then now I'm going to simulate this now. Now this voltage is moving on, right? We will check the response of the system. And also it also taking some time. Okay, so just I'm going to click on first, and then here I'm going to like move a little bit. So now I'm going to update this block and going to simulate this one. Now we can see that we are settled quickly, right? The voltage will settle somewhat quickly, and then we are getting almost 99.11 kilowatts, right? And also we need to check the current of this inverter, right? So here I am going to check the inverter detail. So this inverter voltage, current and power. So I am going to check the nature of the here you can see that we are getting some harmonic, right? Here also you have to check you have to check this current from to the grid, right? So we are getting some harmonic because of some oscillation in this current, right? So we need to rectify that one. So here I'm going to tune this PID controller little bit, and I'm going to update again, and then again I'm going to simulate the model. So we need to check both that profile of that voltage and then this current also. Okay, we need to get the current, right? Current having some less THT, right? So for that we need to check this detail clearly. Okay, so now when comparing with the previous result, we are getting better result now, right, in the current. So but even though we need to check the THT. Okay, so for that I'm going to power GI and go to FFT analysis, and then I'm going to click scope data 2 and selecting current this one. So here I'm going to fix 0.08 and 50 hertz, and then same as the maximum frequency. So number of cycle 1, and then start time is 0.08, and I'm going to display. So here you can see that we are getting around 2.88%, right? So again I'm going to tune the system little bit. Okay, so here again I'm going for here. I'm going to again update this one, and then again I'm going to simulate the model and then check the settlement of the voltage, everything. Okay, but here you can see that we are not getting the proper current, right? Current will be having some harmonics. So here I'm going to fix here and update and simulate. So the designing of that PI controller will be take some time, so you have to should be patient in order to design that PI controller. Now also we are getting some problem. Okay, so I'm going to use so here also you are getting harmonic very high, right? So when adjusting this parameter, right, you will see the variation, right? tuning again and again in order to get the better result for the current quality, right? So here I'm going to adjust a little bit. Because we need to minimize this current oscillation, so then we will get the improvement current quality. Now we have to wait for some time for settlement of that voltage, right? Now you can see that we are getting current, right? Almost that means it have some oscillation around. Okay, it having oscillation, so that's why you are getting this. So you have to adjust slightly and then play again. Again the voltage is oscillating. Okay, slightly increasing and update. So we should avoid this oscillation because it will create problem in the power maximum power point extraction from the PV. Okay, still I'm tuning this PV parameter. Okay, in order to get the better results. Now somewhat okay, we are getting the better result from the PV as well as that power gen that means supplying to the grid also. They are having good quality. So I'm going to fix this value, right? So I'm going to stop this PID tuning process. I'm going to fix the K value. Okay. Now I'm going to test the model for a different irradiation. So initially the irradiation will be fixed here is 1000 watts per meter square, right? So now I'm going to change, that means I'm going to change the irradiation from 1000 to 500 and then you have to check the result. So we will change the irradiation after 0.1 seconds. Okay, and then you will see the response of the system. So now I'm going to change irradiation to 500, and then you have to check the result of the system. Now because of change in irradiation, right, what happened, the current will be reduced to around 57 or 58 amps, and then power you can see that is around 50 kilowatts, right, and also you can see that current, right, current also, grid current also is a decrease, right, and also you can see that there is a power from the inverter, this is power to the grid. Okay, and now I'm going to increase the irradiation to 1000 watts per meter square, and then I'm going to check the result. So here you can see that because of increasing irradiation, it jumped from 57 amps to around 110 amps. So here you can see that PV power is jump from 50 kilowatts to around 99.11 kilowatts, right, and also you can see the change in current and power of the inverter and grid power. Okay, so next process we need to check the THT. So here I'm going to check the THT. So I'm going to click scope data 2 and then click input, and here I'm going to check the THT at 0.06 initially, and then I'm going to check this around 1.99%. So THT is very good for grid current, right, and then here I'm going to change to 0.14, and then check the THT. So for THT also here is 4.29%, so less than 5% only. Okay, so this is a step-by-step implementation of a single stage grid connected PV system. Thanks for watching our videos. Kindly subscribe our channel and also click bell icon for notification about upcoming videos. Thank you so much. Bye bye.